Question 6. A small steel sphere of mass m travels horizontally toward a rigid vertical barrier with speed u. It rebounds in the opposite direction with speed v after an almost instantaneous, perfectly elastic impact. During the collision, a sensor records the sphere's change in momentum. Which expression gives the magnitude of the sphere's momentum change? This question tests our understanding of how to calculate the change in momentum during a collision. Let's start by recollecting the relevant ideas. We know that the momentum of an object is defined as P equals mv, where m is the mass and v is the velocity vector. This means momentum depends not only on how fast an object moves, but also on the direction in which it moves. We also know that the change in momentum, sometimes called impulse, is given by delta p equals p final minus p initial. In other words, we take the final momentum of the object and subtract the initial momentum to find the impulse. Another important point is that momentum is a vector quantity. Because of this, reversing direction changes the sign of the velocity, and therefore the sign of the momentum. Let's get into solving the problem. Before the collision, the sphere is moving toward the barrier with speed u. So the initial momentum of the sphere is mass times velocity, which gives p initial equals mu. After the collision, the sphere rebounds in the opposite direction. Since the direction is now reversed, the velocity becomes negative relative to the original direction. Therefore, the final momentum is p final equals m multiplied by negative v. Now we calculate the change in momentum using the definition. Delta p equals p final minus p initial. Next, we substitute the expressions we found for the initial and final momenta. This gives delta p equals m times negative v minus mu. Both terms contain the mass m, so we can factor it out. Doing that gives delta p equals m multiplied by negative v minus u. We can rewrite this slightly to make it clearer. This becomes delta p equals negative m multiplied by the quantity v plus u. However, the question asks for the magnitude of the change in momentum. Magnitude means we are interested only in the size of the quantity, not its sign. So we take the absolute value of delta p. When we do that, the negative sign disappears and we obtain the magnitude of the change in momentum as m multiplied by the quantity u plus v. So the magnitude of the sphere's momentum change is m times the quantity u plus v. This is our final answer. What did we do? We started by writing expressions for the initial and final momenta of the sphere. Because the sphere rebounds from the barrier, its velocity reverses direction, so the final velocity carries a negative sign. Next, we used the definition of change in momentum, which is final momentum minus initial momentum, and substituted these expressions. After simplifying the algebra, we obtained negative m times the quantity v plus u. Finally, since the question asks for the magnitude of the momentum change, we took the absolute value, giving m multiplied by the quantity u plus v. Now let's address a couple of common misconceptions. One common mistake is using v minus u simply because the speeds are subtracted without recognizing that velocity is a vector. The correct reasoning must come from the fact that the direction reverses, which introduces the negative sign in the final momentum. Another common mistake is leaving the answer as negative m times the quantity u plus v and forgetting that the question asks for the magnitude. Magnitude must always be positive, so the negative sign must be removed by taking the absolute value. Job completed. Let us have a quick summary. Since momentum is a vector quantity, the direction of motion must be considered when calculating changes in momentum. The change in momentum is calculated using delta p equals p final minus p initial. And when a sphere rebounds from a rigid barrier, its velocity reverses direction, so the final momentum has the opposite sign to the initial momentum. The magnitude of momentum change is always positive regardless of direction. Because the question asks for the magnitude of the change in momentum, the final result must be positive.